All right, so last time we discussed smooth category theory. We saw that we can introduce a Check model structure on pre-sheaves valuing any combinatorial left proper model category, which in practice means pretty much everything that we see in practice. More specifically, you would start with either the projective or injective model structure on pre-sheaves, and then do a left pulse localization with respect to all uh, Czech covers, transert with an arbitrary object of your model category V. And the effect of this is to produce a model structure where local objects will be pre-sheaves that satisfy infinity descent, meaning the canonical descent map will be a weak equivalence. So in particular, fibrant objects in this local model structure will be pre-sheaves, say in the projective structure, that will be pre-sheaves valuing fibrant objects in capital V that satisfy infinity descent. And then we saw how perhaps in this new setting we can do what one could rightfully call smooth category theory. And we get some examples. For example, we define vector spaces as a smooth category. And after imposing a notion of completeness and Hausdorffness, we saw how, for example, limits and colimits of vectors, smooth vector spaces work. And basically, we discovered that in complete analogy to how if you take a diagonal functor from vector spaces to families of vector spaces indexed by a set capital I, this diagonal functor has a left adjoint, which is a direct sum, and a right adjoint, which is a direct product. And in the smooth case, when you try to do a similar setup, now taking complete, separated, smooth vector spaces as your category of interest, and capital I will now be not just a seg, but a smooth seg. You can define in a similar manner the diagonal functor. It has a left and a right adjoint, and the right adjoint is what is called smooth sections of a family capital V. So you essentially get smooth maps from I to the corresponding fiber of V. And the left adjoint is what you can call the compactly supported sections. Compactly supported distributional sections. And we also look at the unique and co-unique maps of these adjunctions. We saw that, for example, for the second adjunction, the unique map was, so the co-unique map was simply the evaluation. It took a section and evaluates, it takes a section and evaluates like a point. And the unique map was what is called the constant function map. It takes an element of your vector space and sends it to a constant function valued in this vector space with this value. And for the first adjunction, we saw how the unique map now will be what is called the Gauke function, or more precisely Gauke distribution inclusion. And the co-unique map will be the integration map. So even though it may not be apparently obvious, the integration and distributions and integration and Gauke functions are all categorical concepts. a fact that may not be immediately apparent to somebody who hasn't seen such type of examples before. Okay, any questions about the last time?
Please repeat what is a double V? What is denoted?
What is W?
Double V.
W is a well, in this case, it's just an object in this category. Complete, separated, smooth vector spaces. So you think of it as a vector space, well, with some notion of completeness built in. So the integration map will be literally integrating compactly supported distributions with values in W. And notice, I probably should have mentioned this last time, but maybe I did. In principle, you can it is possible to include top degree differential forms on capital I with values in W, or more precisely, it's not even top degree differential form, but top degree tensor with the orientation bundle of I, what is known as densities, and this embeds into distributions, and this will recover the usual integration of top degree differential forms. So as a special case, you recover integration of differential forms.
In other words, this map is defined as integration of forms, yes?
It specializes or restricts to integration of differential forms in the usual sense when, first of all, when you restrict from distributions with compact support to very special distributions, which I think could be characterized also in some way, but it doesn't really matter. And if you restrict, for example, when you get W to be real numbers, then you just see that your vector space, this vector space here, contains top degree differential forms on I, or more precisely densities, and this recovers the usual integration of densities. But in general, integration of distribution is a really stupid map. If you have a distribution, maybe I should have said this, but if you have a distribution psi, how do you integrate it? Well, you simply evaluate psi. Well, yeah, it's a bit more complicated, I guess, but imagine W is real numbers for a second. Then this will be just compactly supported distributions on I. And you can evaluate such a distribution as a smooth function 1. Because recall that distributions were previously defined as basically smooth. Yeah, so in this definition, we saw that compactly supported distributions are just smooth linear functionals on smooth functions. And a theorem of Schwartz probably says this is the same as a continuous linear map, where continuity is understood in the Whitney topology. Probably should have said Whitney topology. So integration of distributions in general is just evaluation of the function 1. This doesn't quite work with an arbitrary W, so you can use one of the two tricks. You can either replace 1 with a constant function valued in the dual of W, and then you use the fact that the double dual of W will be isomorphic to W, or any other similar trick is going to work. But in general, that's just this integration is kind of tautological, and maybe this reg arrow is slightly less trivial to define because how do you embed top degree differential forms in distributions? Well, you literally construct a linear functional by taking the integral with respect to this density here. So it's the reg arrow, so to say, has some integration in it, at least in the sense of differential forms. Okay.
Is this example of smooth vector spaces written down somewhere, or is it an ongoing work?
Well, it's mostly ongoing work, I guess. I do have some manuscript, which is in a half-ready state, but it's not on archive yet, I guess. So, I mean, I'm happy to show it to you or discuss it with you, but there's no public version yet.
Okay, thank you.
Yeah. Yeah. All right. Let's move on, and probably I should make an announcement. Next week I'm traveling, so there will be no lecture. If you are somewhere near Texas, remember there's an eclipse on Monday, April 8th, full solar eclipse, which I guess I'm going to see because the conference is right next to it. And so next lecture will be next Sunday, April 14th. And presumably in April, we'll have 2 or 3 more lectures. So we are pretty close to being done. So we'll finish defining the Bordism category with all bells and whistles either today or April 14th, next lecture. And then once we have defined the Bordism category, we can define functorial field theory and skate the locality property and the main theorem, the geometric cobordism hypothesis proper. So we are pretty close. I can see not so many of you are left now, so it's probably also a good time to start wrapping things up. All right. So let me explain how the Bordism category can be implemented as a smooth higher category. And last time we also discussed how to implement the non-smooth Bordism category as a symmetric monoidal infinity D category. And if you recall how this worked out, probably I should put for your convenience the description on the left. Yeah, it was right here. So that was 1 week ago. So we discussed how we can define a symmetric monoidal infinity D category of Bordisms. So recall that gamma controls, so we need to define a contravariant functor from gamma times delta D to simply show sets. So we just go in categories and then apply the nerve functor as usual. And if we have some object L and a bunch of simplices M1 to MD, then to such a Geiger we assign a category whose objects we call Bordisms. So what exactly is a Bordism? It's a triple MPC. And M is a d-dimensional smooth manifold without boundary. So just a manifold in the usual sense. P is a map from M to L as a finite set. And previously we discussed how such maps partition M into L components, and you think of those L components as encoding an L tuple of bordisms, and elements inside this L tuple can be multiplied, meaning we can take their disjoint union by post-composing with a map from this finite set to some other finite set. Now, C is what is called a cut grid on M. C consists of, you see in this picture, it consists of a cut tuple on the manifold M, as a single cut tuple for each direction, each of the D directions. And the idea is that the I's cut tuple Ci controls composition in the I's direction. So in this picture, you see a 2x3 grid. So you have 3 cells in the horizontal direction, 2 cells in the vertical direction. So you think of this picture as encoding 6 composable bordisms. And these bordisms can be composed in the vertical direction by removing this horizontal line. And it can also be composed in the horizontal direction in 2 different ways, by removing this line or this line. And the only other condition being imposed is a transversality condition. The transversality condition says if you pick 2 or more different directions, like here I take a horizontal and a vertical direction, and take some cuts in the horizontal and vertical direction, then from the definition of a cut, I already know, say, that each vertical cut partitions the manifold into a negative and positive part. Likewise for a horizontal cut. And the transversality condition says if you pick both, it is possible to partition the whole plane into 4 areas, where the corresponding height function will be positive, respectively negative, for each of the directions. And here you see, like a non-example, if 2 cuts are tangent to each other, then it's not possible to pick such a function. And there is also a regularity condition, which says the regular values of this combined height function form an open neighborhood of 0. So in particular, you do have transversality at 0, and also in some neighborhood of 0. And the other conditions are the same as before. There is also a compactness condition, which says if we discard the colors and just keep what's inside the grid, the interior inside the grid is compact. And there's also a globularity condition, which kind of, let me not recall what that is, but kind of forces the picture to actually look like this. So the 1 bordisms, for example, here in the vertical direction will be collapsed to a point. And this definition is very easy to modify to do everything in smooth families. So now we have this additional parameter, which is a Cartesian space U, capital U. And the bordism category as a smooth symmetric monoidal infinity D category lands in, again, equivalent categories, and then we'll take the nerve. And the only modification now is that, well, M and P are the same as before, but now the cut grid it will be not just a single cut grid, but a smooth family of cut grids indexed by capital U. So for every point of capital U, you have a cut grid C, and as your point moves around capital U, the cuts change smoothly. And what this means in practice is that each cut is specified by some height function, and this function has to change smoothly. That's all that it means. And here's maybe a canonical example. In dimension 1, we can take U to be the parameterizing family will be real numbers. The manifold M will be also real numbers, but now horizontal. So the vertical direction is U and the horizontal direction is M. And inside M, we have two cuts. Here is the zeros cut. The vertical line is the zeros cut, and the diagonal line is the first cut. And that's what I try to express here by saying that C1 is two cuts, and the first one occurs at 0. And the second one occurs at the parameter t, so t is a point in U. So as you move around U, you see an interval of length t. So if you pick some point in U, then the corresponding bordism will be precisely the interval contained inside. So that's your bordism indexed by this point of U. Likewise for some other point. So as U moves around, your interval stretches and shrinks. Then you get a smooth family of intervals. And of course, this should remind you of quantum mechanics, where that's exactly what you call the time evolution. So this is called the time evolution operator. So the smoothness condition for category says Functorial field theory that maps this one-dimensional bordism category into some target. Well, it has to send a smooth family of bordisms given by intervals of length t to a smooth family of values. For example, a smooth family of unitary operators in a Hilbert space, or some similar type of topological vector space or a smooth vector space. And ultimately, it's precisely the smoothness condition is what guarantees the existence of an infinitesimal generator for such a one parameter group of operators. So that's what is called the Hamiltonian. And of course, that's very important. So you can see that this is not just bells and whistles for the sake of adding more stuff to our setting, but it's just something that is forced on us by physics considerations. Okay, any questions about this example or the smooth bordism categories in general?
Dmitri, can you hear me?
Yeah.
So, so this sounds reasonable. I'm still a bit confused because I thought that when you put the geometric structure of Riemannian metrics on one-dimensional Bordisms, and if you then apply a functor and map into Hilbert spaces or something like this, then what you get is if you take an interval of length t, then you get basically e to the minus ith, something like this, right? And this would be the one parameter family that you get for every Bordism. So how does this play into this picture with the smoothness condition?
Yeah, so that geometric structures will come up next, actually, and that's where the actual Riemannian metric will show up. So here, you are correct that, I mean, it's at this point, we don't really have a notion of a length, so that will come in a bit later, yeah.
So what confuses me is, what if we do this smoothness, but then also put on Riemannian metrics? Do we not have two notions of like?
Correct. Of course, you have a smooth field theory and a smooth field theory with Riemannian metrics, one-dimensional Riemannian metrics, and these two give you different. They give you very different answers. For example, imagine you have, in one case you have metric, in the other one you do not. And then your one-dimensional Bordism also maps to some manifold, some fixed manifold X. Then without a metric, you get what is called a vector bundle with connection over X. Whereas if you do have a metric, you get something maybe less familiar. And essentially, it will be a vector bundle on the space of germs, one-dimensional Riemannian germs inside X, or something similar. So these answers will be very different. So in particular, if you don't have a map to X, without a metric, your functorial field theory, I mean, since all smooth intervals are ultimately the same, you will basically just see the identity map here. So that will be kind of tautological. Whereas if you do have a Riemannian metric, then you will see they will not be isomorphic, and you will actually see a non-trivial one-parameter group. So the case when you don't have a Riemannian metric, that's basically a topological field theory, but with a smoothness condition. So what it means is if you start classifying such gadgets, well, if you didn't do scuff and smooth families, you would simply see a dualizable vector space, so a finite dimensional vector space. But if you start doing scuff and smooth families, you will see a smooth family of such Bordisms would have to map to a smooth family of vector spaces. But well, in our case, I guess without a Riemannian metric, there's only a single smooth family. So again, you don't really see much new. However, it is possible. So maybe I should have said that this is a point where defining the space of functorial field series of dimension D with some geometric structure S and category of values V. Well, if you define it as the internal Hom from the Bordism category to V, well, this internal Hom is itself a smooth infinity. Well, it is a smooth infinity groupoid, I guess, ultimately, but we don't know this yet. And as such, it will at least see the smooth structure in V. So even if you don't have any geometric structures, once you start talking about the whole space of functorial field series, you still do get to see non-trivial smoothness inherited from capital V. Only if you replace internal Hom with just a mapping space, then you see to see any difference. Yeah. Yeah. So yeah, so most of the interesting stuff will show up in the presence of a Riemannian metric. Yeah. Or any other non-trivial geometric structure.
Thanks.
All right, more questions? All right, so maybe let me move on to the topic of geometric structures. How we define them in general, and some maybe mention some subtleties. And let me first do it without talking about smooth families. It will be a bit easier to explain. And perhaps one of these things to explain here is how we arrive at such a definition. And what exactly do we need from a geometric structure? So if you look at the picture of bordisms and their composition, let me pull out some nice picture for you guys, if I can find it. Ah, here is one, yes. So imagine this is your bordism, and you want to put maybe a geometric structure like a Riemannian metric or principal G bundle with connection, or maybe some kind of a differential form. And you are wondering, like, what's the general setup? So we don't want to introduce ad hoc definitions for every possible case. What exactly is a general what are the general requirements we need to impose on geometric structures? How can we define them abstractly? So maybe the first observation to make is that for any d-dimensional manifold, any d-dimensional manifold could be the ambient manifold of a bordism. So in particular, for every d-dimensional manifold, you want to be able to talk about the object of geometric structures on that fixed manifold. So for example, you can talk about the set of Riemannian metrics on a smooth manifold, or the set of, let me see what examples I gave you here, the set of other like conformal or symplectic structures, or maybe the set of maps from your manifold to some fixed target manifold T. That's what is called a sigma model in physics. Or perhaps a set of orientations on your manifold. But there are also geometric structures which don't really naturally form a set, but rather form a groupoid, or perhaps some other higher categorical structure. And maybe the most canonical example would be the groupoid of principal G bundles with connection over your manifold, and morphisms will be connection-preserving isomorphisms. In physics, this is called the groupoid of gauge fields, or more precisely, gauge fields and gauge transformations. And you cannot really reduce this to this type of groupoid to any set, because if you take well, first of all, in physics, you really do want to be able to talk about gauge transformations, so you have to incorporate them in the picture. And if you try to say get rid of the groupoid structure and take maybe isomorphism classes of principal G bundles with connection, then it's going to be problematic because such isomorphism classes cannot be glued. You cannot glue them. So if you have one isomorphism class here and another isomorphism class here, in general, there is no unique way to glue them to an isomorphism class. Maybe the easiest example is when you glue a circle out of a two half circles, like this. So you have one half circle, another half circle. They overlap in a disjoint union of two intervals. And the set of isomorphism classes of principal G bundles on a half circle has a single element, the trivial principal G bundle. That is also true if you have a connection. So you have a single isomorphism class on each half circle, also on each interval there is a single isomorphism classes. So the whole gluing gate is trivial. But of course, on an actual circle, you have tons of non-trivial principal G bundles with connection. In fact, you can classify them by taking the holonomy around the entire loop, and the conjugacy class of this holonomy will be an invariant of your principal G bundle with connection. So what this tells you is that passing to isomorphism classes in this groupoid just doesn't make sense. You will not be able to glue bordisms equipped with isomorphism classes, period. So it is truly necessary to keep the whole groupoid around, not just its isomorphism classes. Probably one more example I should have mentioned to you, and now there is no space to put it, but maybe example F would be, say, higher gauge fields. And again, this is not generality for the sake of generality. There are plenty of examples in physics, like B field or the so-called C field in supergravity. These are encoded by bundle gerbs with connections, or like the Ramon field, which is encoded by a co-cycle in differential K-theory. And these don't form a groupoid anymore, but a higher groupoid. Like B fields form a true groupoid. C fields form a three groupoid. Ramon fields form an infinity groupoid. And there's just no way to get rid of such higher categorical structure. So if you want to work with Ramon fields from string theory, you do have to consider infinity groupoids. And that is precisely the reason why to a smooth D manifold, we want to assign a whole simplicial set of geometric structures. So the simplicial set can encode an ordinary discrete set. It can encode a groupoid via the nerve construction, and it can encode higher groupoids, including infinity groupoids. So this level of generality is dictated by specific considerations from physics. Okay, so we more or less agree that, I hope, for every d-dimensional manifold, you want to assign a simplicial set of geometric structures on that manifold. Now, what else do we need in order to define a category of Bordisms that can be glued together? If you stare at this picture for a while, you can see that, for example, if you have such a Bordism, well, part of the structure of a Siegel space is that you are allowed to throw away stuff. For example, you can discard the third cut and the second cut, and what remains will be just this Bordism between 0 and 1 here. And the other thing I mentioned is that when we talked about morphisms in this category of Bordisms, morphisms were cut respecting embeddings of Bordisms. And here was a picture. So you have one Bordism and it embeds into another Bordism. And the embedding really doesn't change anything except that it can potentially expand the colors. So the part located here and here can perhaps be expanded by this embedding. So the main part, the core, doesn't change, but the colors can expand. Now, if imagine both of these guys are equipped with a geometric structure, then we certainly do want that for such an embedding, the geometric structures must coincide. And so mathematically, this would be expressed by saying that if we create a geometric structure on the bigger Bordism and restrict it along this open embedding, we get a geometric structure on the other Bordism. So the takeaway from here is that you do want to be able to restrict geometric structures along open embeddings. Because open embeddings is precisely what you have in this category of Bordisms. You do allow expanding colors, and in order to be able to talk about geometric structures, you need to be able to restrict them along open embeddings. So this motivates the choice of morphisms in this, the type of structure where you have a simplicial set assigned to a smooth D manifold, and to every open embedding, you have a restriction morphism. Well, that's precisely a pre-sheaf. So we see that we naturally arrived at the idea that geometric structures should be a simplicial pre-sheaves on the category of d-dimensional smooth manifolds, and morphisms are open embeddings. And there is one more final condition, which is, of course, related to gluing of Bordisms. Imagine somebody provides you with a geometric structure on the Bordism between 0 and 1, and another geometric structure on the Bordism between 1 and 2. Now, as we discussed before, the Bordism between 0 and 1 is not really between 0 and 1. It also has the colors to the left of 0 and also to the right of 1. Like this. And likewise, the Bordism from 1 to 2 also has colors, a little color to the left of 1 and a color to the right of 2. And these colors are going to overlap around in an open neighborhood of 1. So where they overlap, the geometric structures will match. More precisely, you will apply the restriction map along the open embedding of this open neighborhood into the whole Bordism. and the geometric structures will match. And what you want from the gluing is that you do have a geometric structure defined on the whole boardism, like this. So there should be a unique geometric structure whose restrictions to this part and this part are as indicated. And of course, you will immediately recognize here the sheaf condition. The sheaf condition is precisely what you need in order to be able to glue geometric structures. So let me clean up the picture. So that motivates our definition that a d-dimensional geometric structure is just an infinity sheaf on the side of d-dimensional smooth manifolds with open embeddings as morphisms. And that's basically the first approximation. We'll refine it in a second. Let me immediately address some obvious variations. One variation is that smooth manifolds can be replaced by Cartesian spaces.
Please may you review a bit more about open embeddings again. I'm trying to understand some intuition behind of this term.
So what about them? Sorry, what is an
About
open embedding?
Yes. On the pictures of boarding.
Oh, well, the open embeddings I was talking about would be if you glue two boardisms. Let me maybe somewhere here draw a picture. So when you glue two boardisms, in fact, we do have a picture maybe which is nicer. Oh yes, maybe here. Yeah, here we talk about boardisms as co-spans and how you can glue boardisms as co-spans in this picture on the left. And we discovered, if you recall, that when we talk about boardisms as co-spans, the co-span was embedding an open neighborhood of the cut. So this, when I draw a circle, two circles with a little fuzz, this fuzz is meant to indicate there are actually two-dimensional manifolds embedding into this boardism and this boardism here.
As I understand, field theories lives there on the circles, yes?
So say again?
As I understand, field theories are located on the circles, yes? From some physical intuition, yes?
What you will assign to a circle will be a space of skates in some physical theory. And what you assign to a boardism will be a time evolution map from the space of skates associated to the left, to the domain, to the space of skates associated to the codomain. So what is being assigned to these circles will be spaces of skates, like in the two-dimensional picture here corresponds to a string theory. So you literally think of those guys as strings moving in space-time. And to such strings moving in space-time, you assign a space of skates. The space of skates of a string, if you want.
And open embeddings is just embeddings into bigger space of states, yes?
No. The boardism itself, I mean, you think of this boardism as basically expressing a movement. Here, for example, two free strings move in a space-time and they somehow come together and merge at somewhere at this point, and they merge into a single string. And to such a movement, you have a time evolution operator corresponding to such a movement, which will be a linear map from the space of states associated to true strings to the space of state associated to a single string. So this Bordism is meant to express a physical process where two strings come together and merge in a single string. This is kind of similar to how Feynman diagrams work when two particles come together, merge in a single particle, and continue as a single particle. Of course, this is not a Bordism here. This is what is called a Bordism with defects. And that's something we haven't discussed yet. But for string theory, you do have such Bordisms, ordinary Bordisms without defects, which include this process when two strings come together and merge.
I understand.
Okay, more questions? Okay, so let me just say, yeah, the equivalent versions of the cycle is one where manifolds are replaced with Cartesian spaces. And this is basically works. So the reason those sites are equivalent is because of the existence of good open covers. Good open covers. The other thing is that open embeddings, if you want, you can replace them with local diffeomorphisms, also known as Étale maps. Have there some other name, I don't know. And the reason this works is because any local diffeomorphism is locally an open embedding. And because they are working with sheaves, that means there is ultimately no difference. Now let's introduce maybe a bunch of examples of geometric structures. I already mentioned Riemannian metrics. So the corresponding pre-sheaf will send a smooth d-dimensional manifold M to the set of Riemannian metrics on M. And an open embedding from M to N will be sent to the restriction map that takes a Riemannian metric on capital N and restricts it to the open subset capital M. There are many other geometric structures like conformal, symplectic, compact, complex structure, Kähler structure, maybe a Riemannian matrix with various restrictions on curvature, Ricci curvature, scalar curvature, sectional curvature, positive, negative. You pick your favorite. The other examples I wanted to mention is a sigma model. In the sigma model, a smooth manifold M will be sent to the set of smooth functions from M to T, where T is a fixed manifold. Typically, it could be the space-time, for example, the space-time. Another example would be various topological structures, like you can send a smooth manifold M to the set of orientations of M, or the groupoid of spin structures. Or you can maybe send it to the true groupoid of string structures. So these are topological structures. or the higher gauge fields, which are defined mathematically as bundle gerbs with connection, or co-cycles in differential case area. And the one of the main physicsy examples, I guess, is the gauge fields, the groupoid of principal G bundles with connection over M. Morphisms are connection-preserving isomorphisms. Given such a principal G bundle with connection, you can restrict along open embeddings to get another principal G bundle. Connection-preserving isomorphisms restrict along open embeddings to some other connection-preserving isomorphisms. Yeah, so I hope this rich variety of examples convinces you that basically we can handle pretty much any geometric structure you may need in physics. Okay. Any questions about this definition or these examples? Okay, maybe let's now move on to geometric structures in smooth families. And the definition is going to be basically a complete replica of the previous definition, except that now everything happens in smooth families. So instead of the cycle of d-dimensional manifolds and open embeddings, we are now looking at the cycle of smooth families of d-dimensional manifolds and smooth families of open embeddings. So what exactly is a smooth family of d-dimensional manifolds? Say indexed by some space or smooth manifold U. Well, one way to define it is to say we have a submersion with d-dimensional fibers. M over U. So if you pick a point in capital U and take its fiber, the fiber will be a d-dimensional manifold, and you think of it as the open manifold, as the smooth manifold, smooth d-dimensional manifold, indexed by the point here. And now how should we deal with morphisms? Well, morphisms will be commutative squares. So here is one object, one smooth family. Here is another object, so another smooth family. These smooth families can be indexed by different manifolds. And a morphism will be a commutative square. So first of all, you specify what happens at the level of indexing manifolds. Where does U map its points? And then the only other condition is that this map F on total spaces, it is a fiber-wise open embedding. So what does it mean exactly? It means if I pick any point in U, in capital U, and I take the corresponding fiber over this point, MU, it's a fiber over U, then since this diagram commutes, this fiber must necessarily map to the fiber of capital N over f of u. Oops, g of u, sorry. And now the color is incorrect. Well, too bad. And the additional condition we are imposing this is that this map here is an open embedding. That's how you define everything in smooth families. Okay, any questions about the definition? Oh, I should have probably, since I mentioned it's a site, I should have told you what the cognitive topology is. But let me just move. Oh my goodness, it crashed. Okay, so moving stuff also crashes. One moment, let me restart. Okay, so I found the other functionality that causes crashes, and that's moving stuff. I guess moving it outside of the boundary or whatever. Okay, can you guys see the nodes again?
Yes.
Great, thanks. Okay, good to know that moving stuff causes crashes. I will avoid also this functionality now. Okay, but that does leave a question of how do I insert some space? Maybe I use some other functionality like this. Ah, this worked. So the psych structure tells you how how covering families are defined. And the way they are defined is you have a collection of morphisms. And you declare it to be a covering family. If, so let me call this Fi and Gi. Fi and Gi are open embeddings. Notice that neither condition follows from the condition of the fiber-wise open embedding. That's different. So here you have to state it separately. And the covering the maps Fi is a covering family of M. N. So it is an open cover in the usual sense. So the union of the images equals N. an open cover in the usual sense. So covering families are given by open embeddings on total spaces and base spaces that are covering on the total space. There is no condition imposed on the base space. You don't have to be covering on the base space. Okay, so that's how the cyc structure is defined. So let's now see how some of the geometric structures can be translated into this setting of families. And basically, all the constructions we are going to use will be using the fiber-wise constructions, and primarily, since everything is basically defined in terms of the changing and co-changing bundle, the corresponding constructions and families will be using the fiber-wise changing and co-changing bundles. So the way it's defined, if you have a family M over U, given by some projection map P, you look at the induced map of changing spaces. The changing map of P goes from the changing bundle of M to the changing bundle of U. And this is a morphism of vector bundles that has a kernel. And the kernel will be some capital V. So capital V is the some bundle over M. That's known as a vertical or relative changing bundle. And now every single definition from differential geometry you can repeat in the setting of vertical changing bundles. So for example, a Riemannian metric used to be defined as a metric on the changing bundle. And now you can define it as a metric on the vertical changing bundle. And this immediately gives you what is called the fiber-wise Riemannian metrics. So you really should think of those as Riemannian metrics on each Riemannian metric on each fiber. And the only other condition is as you move around the fibers, the metric changes smoothly. And the other definitions can also be repeated in the same manner. For example, you can talk about fiber-wise principal G bundles with a fiber-wise connection. Depending on what your preference is for the definition of a principal G bundle, but typically a principal G bundle is defined in terms of a what is called a connection one form, which is a differential one form on the total space valued in the Lie algebra. And guess what? Now, instead of differential forms, you use what is called fiber-wise differential forms. So fiber-wise differential forms are multilinear antisymmetric maps from the fiber-wise changing bundle. So you basically put the fiber-wise adjective in front of everything and you get the correct notion. Let me, however, emphasize here that a fiber-wise principal G bundle with connection on M over U is not the same as a principal G bundle over M. And the reason for this is that a principal G bundle over M, for example, you can define the parallel transport map for any path in M. In particular, this path can go from one fiber to another. Whereas for a fiber-wise principal G bundle with connection on M over U, you can only define a parallel transport map for a path that scans that is completely inside some fixed fiber over U. So you can only transport things within a single fiber. So that's less data. And so fiber-wise principal G bundle with connection on M over U is not the same as a principal G bundle over with connection over M. So that's just not the same data. And this, of course, has to do with that here the connection one form need not be a fiber-wise form. Whereas here it is required to be a connection one form is required to be a fiber-wise form. And one example scales essential unchanged. If you want to do sigma modeling families, well, there's basically only one thing you can do. A smooth family M over U, you send it to smooth maps from M to T. So here, there's no difference between fiber-wise, smooth function is exactly the same as simply a smooth function from the total space to T. But that's a special property of this example.
But for the sigma model, you could also make it into a simplistic set, right?
You mean this gadget here, or?
Exactly, yes.
And
By just
so,
taking the product with this smooth n simplex thing.
yes, but this would be like basically a topological sigma model, because if you think about what it means to incorporate those simplices, all of a sudden, once you have those simplices in the game, that means that if two maps from M to T are related by a smooth homotopy, then the values of the corresponding functorial field theory must also be related by some categorical homotopy, which means in particular they will have to be isomorphic. Which is, I mean, of course, that's fine. There is such a thing as a topological sigma model, but it will be a topological field theory. Yes. So, for example, gauge graph Wittering theory is an example of a topological sigma model. It's a topological sigma model when the target, capital T, is the de-looping of a discrete group G.
Where do these fiber-wise principal G bundles appear in the wild, sort of, or maybe to put it bluntly, what's the use of them?
Well, it's exactly what you need to define the, say, Young-Mills theory as a functorial field theory, because as part of the definition of what it means to define the Young-Mills, so Young-Mills theory uses principal G bundles with connection as geometric structures. And so, in other words, roughly speaking, such a theory, given a bordism equipped with a principal G bundle with connection, it sends it to some value. And the condition you must impose is that if the principal G bundle with connection changes smoothly, the value must also change smoothly. But what does it mean exactly for a principal G bundle with connection to change smoothly? And this part E gives a precise answer. It means that the smooth family, you have a smooth family of fiber-wise principal G bundles with connection on the smooth family of bordisms. So
Okay.
that's precisely how the Young-Mills theory will be Young-Mills type theory will be defined in any setting. Yeah. Okay, more questions?
So these fiber-wise principal G bundles are more general objects, right?
More general than what exactly?
Than principal G bundles on with connection on M.
So if you take capital U, the indexing manifold to be a single point, so M over a point, that's just a family consisting of a single manifold M, then a fiber-wise principal G bundle with connection on M over a point is precisely a principal G bundle with connection in the usual sense, just on M. So in case when U equals a point, you recover the usual non-fiber-wise notion. But in general, that's like this refinement to a fiber-wise geometric structure is in principle not automatic. And you could imagine, for example, that instead of this definition E, I could have taken the definition E prime, where I took simply principal G bundles with connection over M. And that would also give you a pre-sheaf on this site. And it would be a legitimate example of a geometric structure. When you just take this right side, which we know to be not the same as the left side. So what's wrong with this choice? Basically, the only thing that's wrong is that it doesn't give you the, it allows you to, it has too much information. Information that's basically going to be redundant in the constructions. And like you don't want to specify this extra information when you specify what it means to have a smooth family of principal G bundles with connection. But yeah, this could be definitely another choice. And if your capital U is a single point, both sides will be equal. So without families, these two guys are the same. And it's only when you start looking at things in families that a difference emerges. Okay. So let me now explain how the Bordism categories with geometric structures can be defined in general. So the input data to the construction now will be different. Let's go back to the previous construction. So our previous input data was simply a dimension D. And now the input data will be, of course, much more. It will be a dimension D and a geometric structure. So that's the input data now. And given this data, we construct, I guess in the paper it's actually called S. And now all of a sudden I start to call it G. No, sorry, G is a really bad letter because G conflicts with. So let me just call it S. So given such an input data, we can define the smooth symmetric monoidal infinity D category of Bordism, so dimension D, equipped with a geometric structure S. And how exactly does it work? Well, let's compare with the previous construction. We will be constructing basically a functor of the same type, but now there will be some changes. And one change is that instead of factoring through ordinary categories like we get here, so here the category that we ended up constructing was a category whose objects are bordisms, and morphisms are embeddings, open embeddings of bordisms with some properties. Here it will be different. It will be a simplicial category. It will have a simplicial set of objects and a simplicial set of morphisms. And so the way you extract an ordinary simplicial set from such a category will be via the diagonal functor. So the diagonal functor takes a simplicial category, converts it to a simplicial object in simplicial sets. That's basically the Siegel type construction, and takes the diagonal to extract a simplicial set. So now, instead of defining a set of objects, I have to define a whole simplicial set of objects. So previously, objects were just triples M, P, C, which were encoding an ambient manifold M is partitioned into some disjoint components, capital P, and capital C, the cut grid, which sliced it up in some elementary cells, which are the actual bordisms. And it had to satisfy some conditions like transversality, compactness, globularity, and everything had to be in smooth families over U. So now we have a geometric structure in the game. So to any such triple MPC, we have a whole simplicial set of geometric structures that we can place on the corresponding bordism. So recall that M is our ambient manifold where all the cuts are taken. And we have this, everything is now in families over U. So the total space of the family will be M times U, projecting over U. And the simplicial set of geometric structures on such a smooth family of bordisms will be S evaluated at this smooth family. And since MPC can be arbitrary, we take the disjoint union over all triples MPC with these properties that I talked about here. If this definition confuses you, maybe one observation you should make is that one special case of a geometric structure is the terminal geometric structure. Let me denote it 1. So 1 of any object in the side will be the terminal simplicial set, which is delta 0, a single point. And in this special case, the simplicial set of objects was defined as a disjoint union over all MPC S of M times U over U. And I'm really sorry, and I guess M is now a bit ambiguous here. Let me rename the total space. And now why? Okay, the total space to capital T, because it's really a different entity. So we have a disjoint union over all MPC of a point, a single point, delta 0. So that's basically a disjoint union of a collection of points is just a discrete simplicial set corresponding to all possible choices of the triple MPC. So it's quite literally the set of all such triples, interpreted as a discrete simplicial set. And of course, this is precisely the set we defined here in the previous setting. The set of objects was previously defined exactly like the set of such triples. So you see that in the case of a trivial geometric structure, the terminal geometric structure, meaning basically there is a unique geometric structure on any smooth family. So in other words, there is a trivial choice of such a structure, no structure meaning. Then the simplicial set of objects degenerates to precisely the set we defined previously. Now, if the geometric structure is not trivial, then for any choice of such a triple MPC, which encodes a bordism in the previous sense, well, let me not scroll back to the same picture, but imagine a picture of a bordism here. For any such choice, you have a whole simplicial set of geometric structures. That's why we take these simplicial sets here. So that's how you construct the simplicial set of objects in this category of bordisms. And the simplicial set of morphisms will be constructed in basically a very similar fashion. You will take a disjoint union, taking over all possible morphisms. And I guess I didn't say what morphisms are here. I probably should have done it. So morphisms will be open embeddings open embeddings from M to M prime compatible with P and C. So what it means is that if you pull back C prime along this open embedding, you get C. If you pull back P prime, you get P. And also the image of the open embedding contains the core of this bordism in the codomain. So let me call this maybe F. And we can say F star C prime equals C, F star P prime equals P, and the image of F contains the core of this bordism M prime, P prime, C prime. Maybe I should. So these three conditions are what a morphism is. So let me call this F. So now when we define a simplicial set of morphism in the setting of geometric structures, we again take a disjoint union over all possible morphisms in the usual bordism category. And for every such a set of morphisms, we take the simplicial set of geometric structures on the codomain. Again, if S is a trivial geometric structure, you will see just a discrete simplicial set on the set of morphisms in the defined as previously defined. So in this setting, you clearly see you recover the previous definition. But now, if you do have non-trivial geometric structures, and incorporating this simplicial set of geometric structures on the codomain provides you with the correct simplicial set of morphisms. At this point, you may be wondering why on the codomain and not, say, on the domain. And this has to do with how the source and target maps are defined. And the source and target maps are very easy to define. The target map will simply take let me see if I can reconstruct this orange color. Yeah, so the target map takes one of those summons here and sends it to, yeah, it's not the same color, sorry. And sends it to, so let's record like objects are disjoint union, overall M's. And let me maybe pick a different. Let me use double primes just to distinguish them from the left side. Then the target map, the bottom map, will simply take the component indexed by this F and send it to the same component where M double prime, P double prime, C double prime is equal to M prime, P prime, C prime. Whereas the source map is a bit more interesting. What the source map is going to do, it will take this summoned and first is going to restrict along F or pull back along F, landing inside of S, evaluating at M times U, so without prime. And then you send it to the disjoint union here by mapping it to the component indexed by the triple MPC. So you see, for the source map, we have to restrict along this open embedding of Bordisms, which let me show you as a geometric picture. No, that's a bad picture. Oh, here. So here's you see on the right, a picture of a morphism in the Bordism category. So an open embedding, like basically what it does, it expands colors. And according to this formula, the simplicial set of geometric structures that only lives on the target, the codomain. So the geometric structure lives here. So this codomain will have a geometric structure. And according to the formulas for S and T, if you want to take the, if you have such a morphism with a geometric structure on the target, well, then the target of the codomain of such a morphism can be obtained simply by discarding the domain and taking the codomain with its geometric structure as a point here. Whereas if you want to take the domain of such a morphism, what you do is you first restrict the geometric structure along this open embedding to the domain, and then you discard the data of the codomain here. And that's exactly what is expressed by this composition here. So first, you restrict along the open embedding F. you restrict to the domain, and then you include the domain inside this simplicial set of objects. So we constructed a simplicial category that, in the case of a trivial geometric structure, recovers precisely the category of Bordisms we defined here with the same objects and morphisms. So for a trivial geometric structure, we recover precisely this category here. But more generally, we'll see some simplicial category that incorporates geometric structures. And that's how things work. That's how you define a Bordism category with geometric structures. Okay, so I think that's a perfectly good time to stop because the next topic will be isotropies, and that's maybe a new topic. So I think that's it for today, and let's see if there are any questions left.
No question regarding the lecture, but in the beginning you said you had notes on this smooth category theory thing and functional analysis.
Well,
You-
I only have like an unfinished draft of a manuscript that explores some properties of the category of complete, separated, smooth vector spaces. And basically, what it discusses is the what is called a star autonomous category of such. And in particular, there are true monoidal structures and true closed structures, true internal Helms. So it discusses their properties and the properties of the duality functor, and how maybe to compute some elementary examples. But right now there is not much else, and the manuscript is not in its final stage because we decided to generalize it to the because we'll eventually need a version for supermanifolds to include supersymmetry and a version for sites used in derived differential geometry. So we haven't generalized it yet to that setting. So right now everything is in terms of Cartesian spaces. But if you are interested, I can send you a copy. Probably it's not a problem.
Yes, that would be nice.
All right. Okay, more questions? Okay, then I guess I'll see you guys in 2 weeks, right? So there is no lecture next week. And in 2 weeks, we'll discuss the very final ingredient, isotropies of Bordisms. We'll discuss what motivates them and why do we need them. It's pretty essential because that's basically what's responsible for generalizability. That's very important for the GCH. And once we define isotropies, we will be ready to define and state the main theorems. So that will hopefully bring the course to an end. Well, unless you guys have some further desires or whatever. But I guess everybody must be pretty tired, and we have been going on for more than 5 months now. 5 months, so that's a lot for a class. So perhaps bringing it to a close would be a good idea. Okay, so that's it for today, and thanks for listening.
Thank you.
Thank you.
Bye.
I'll see you in 15 minutes, right? We have.
Let's see. So I will be busy from noon till maybe for 20 minutes from noon till noon 20. So perhaps maybe half an hour after noon. So in 50 minutes maybe from now. Yeah.
Okay, right. Great.
Yeah.
Thanks for the lecture, and see
Yeah.
you.
And plus or minus 10 minutes roughly. So I can finish either 10 minutes before or 10 minutes after. So you should expect maybe it's not a precise timing, but roughly 50 minutes from now. Yeah.
Okay, no problem. Okay,
Okay. Yeah. I'll see you soon. Bye.
bye.